Welcome, radiant viewers of Science and Spirituality. When life first appeared on Earth, our planet's atmosphere consisted mostly of organic gases like CO2, methane, and very little oxygen, similar to the present atmosphere on Mars or Venus today. But about 2.7 billion years ago, single-celled algibacteria began to reconstruct our planet's surface. This algibacteria invented a very sophisticated process called photosynthesis and began to mop up CO2 from the atmosphere and replace it with oxygen. If not for this bacteria with sophisticated solar plants inside their cell membranes, there would be no you or me, no other animals, and not even plants, none of the diversity of life we see today. Photosynthesis is the central chemical process on Earth. Life on Earth is effectively solar-powered, and all of our energy and food come from photosynthesis. So it's important we look at this phenomenon and examine how we may possibly use it to enhance the sustainability of our planet. Dr. Greg Engel is an assistant professor with the Department of Chemistry at the University of Chicago, USA, and a physical chemist. Last week on Science and Spirituality, Dr. Engel described the flawless quantum design that bacteria and plants use for light harvesting, a process which he discovered. For his contribution to the field in 2007, Dr. Engel was named by Scientific American, a leading US science magazine, as one of the top 50 research leaders of the year. In a moment, Dr. Engel will share with us his in-depth thoughts on photosynthesis, but first he will give us some background on this important life-giving process.
Could you give us a brief description of how the sunlight first enters a green plant?
Oh, absolutely.
Into glucose.
Absolutely. Photosynthesis is the process by which plants make their food. Inside the leaf of a plant or in a photosynthetic bacteria, there are protein structures that contain chlorophyll. And the sunlight is absorbed by those chlorophylls, and it excites them, and they move into a more energetic state. And then as one chlorophyll becomes de-excited, the next becomes excited, and it can move this excitation to a very special protein complex called the reaction center. And as its name implies, this is where the chemical reactions in photosynthesis take place. This is the first biochemical step of photosynthesis. Up until this point, you should really think about it more as physics. It's light exciting a molecule, and then it's the wave function allowing the energy from this excitation to propagate to the reaction center. Once the energy reaches the reaction center, then you have charge separation. And this is where the electron hops down a chain towards a quinone, while the positive charge stays on the first chlorophyll. This is the most important part of photosynthesis. This is how you move the energy from the light into chemical energy. Once we have the charge separation, the quinone can move away and power the rest of the photosynthetic apparatus, which creates glucose through the Calvin cycle. There are two main parts of photosynthesis to think about. One is the biochemical side, the Calvin cycle, for which Calvin won a Nobel Prize elucidating the detailed processes of this biochemistry. And then this initial part, which is much less well understood, for how the light moves from its initial point where it's absorbed all the way to the reaction center without losing energy, without losing all of the energy.
So can you tell us a little bit about your research? What has been discovered?
We discovered a new wave-like mechanism of energy transfer. This is hard to think about because it's a purely quantum mechanical phenomenon. But the way the energy seems to move is it occupies many states at once. So it's more like pouring water into the maze, where the water flows through all pathways and then drains out the other side. It doesn't have to explore one tunnel or another, but rather it can explore them all at once and feel all the different paths around it in order to make it to the reaction center very quickly and very efficiently. As energy moves from high energy to low energy and gives off small amounts of energy to heat, that directs the energy towards the reaction center, the lowest energy state. But what's different about this is you can move these very high energy excitations to the reaction center without ever losing one. And there's enough energy here to split water, which is how photosynthesis happens. And yet it never breaks apart the protein. There's enough energy to blow apart the entire apparatus, but you never lose a full quantum of energy. It's extraordinary that the energy makes it to where it's going 100% of the time. And that's what we find most exciting.
So there's wave-like characteristics. It's like a constructive interference of waves.
That's exactly what's happening. That you have a wave-like character based on the excitation from the light. And usually you would expect this wave-like character to disappear very, very quickly. And then you have a classical sort of hopping mechanism that we discussed before. But instead, the protein structure in these complexes protects this coherence, this wave-like aspect of the system, long enough that the energy can then move in a wave-like fashion and test out many different possibilities at once. The quantum efficiency of this process is almost perfect, far better than anything that we can build. And that's really the driving motivation to understand this.
Coming up next, more of our interview with Dr. Greg Engel on the fascinating process of photosynthesis. You are watching Science and Spirituality on Supreme Master Television. We'll be right back after some brief messages. This is Science and Spirituality on Supreme Master Television. We are speaking with Dr. Greg Engel of the University of Chicago in the United States on his work to better understand the nature of photosynthesis and how the process transfers energy so quickly and efficiently. Is there any special arrangement around light absorption centers that nature takes advantage of in order to optimize the process of the energy transfer, namely to prolong the lifetime of the coherent wave-like energy transfer?
Absolutely. The structure of these complexes is extraordinarily important to this process. It's very interesting that this differs from man-made materials. To have coherence in man-made materials, you need long-range order because the excitations are very delocalized. Photosynthesis is fundamentally different in how it works. It has very localized excitations. They're more of molecular excitations than they are delocalized excitons. The aspect of the structure that allows the long-lived coherence is not long-range structure, but rather it's coordinated motion in the protein, so that you have one chromophore and another chromophore, and you may have an alpha helix in a protein that links them. And as that alpha helix moves, the energies of these two chromophores move in a synchronized way. So it's actually the dynamics of the motion that allow this long coherence time and avoid moving to a more classical dynamics and take advantage of these quantum mechanical phenomena. So it's the structure and how the elements of the protein are arranged in the neighborhood of the chromophores that allow the long-lived coherence. And this is a fundamentally different engineering approach than what we use in man-made structures to get long coherence times. And I think this is actually very exciting because it allows us to have long coherence times and quantum mechanical effects without the long-range order that creates these big delocalized systems. So you can get the best of both worlds. It can be a very small complex, but you can still have these large quantum mechanical effects in play.
Do you think it is significant for this wave-like coherent quantum effect that the energy transfer in photosynthesis is realized through the exciton, which is a closed bound electron-hole pair, and its total electric charge is exactly zero? So because it is exciton, it cannot be affected much by an external electric field.
I think there's a very important aspect of this, that when you have charges that separate, then you see strong electric fields. If you keep the electron and hole close to one another, then it's effectively neutral, and it's much easier to limit its interactions with the outside world. And I think that goes directly to how this bacteria or plant protects the coherence in the system. That if it were a lone charge and just an electron or just a hole with a positive or negative charge, then I don't think there would be any way to protect these systems from dephasing. Though as we study more, perhaps nature will prove me wrong with another ingenious scheme for how to do this. But I think that this is a fundamentally important part to this specific photosynthetic process, that the electron and hole being very close to one another seems to be extraordinarily important for how you might be able to isolate this excitation from the outside water bath and other charges and charge residues inside the protein.
Dr. Engel was asked to briefly outline some basic features of quantum mechanics that touch on his research on photosynthesis.
Quantum mechanics grew out of the early part of the 20th century, as people were trying to describe the physics of the very small and the very light. So understanding how photons, light interacts with atoms and molecules. And what they found was the classical description wasn't sufficient. Quantum mechanics is a mathematical description, a purely abstract mathematical description that apparently mirrors nature perfectly. We're trying to use this quantum mechanical mathematical apparatus to understand exactly how plants produce and move energy so efficiently. We've stumbled upon a mechanism that we can't understand through any mechanism other than this mathematical description. And we found that it can be much more efficient than our other ideas for how energy moves.
Dr. Engel's discovery provides probably the first experimental evidence of a quantum nature of an essential macroscopic biological process. Studying other biological processes are finding some evidence of quantum phenomena in areas such as the conversion of chemical energy into motion, magnetoreception in animals and birds for navigation, eye and brain dynamics, and perhaps even in evolution, where they are called fossil gaps. However, in all these examples, the quantum nature of these processes is not settled as in the case of photosynthesis. Next week on Science and Spirituality, Dr. Engel will discuss how photosynthesis can help in our endeavors to make our planet more sustainable. Now please stay with us for words of wisdom coming up next, right after noteworthy news. So long and God bless.